Hi students, today we are discussing writing lines in 3-space as a function of time. We can do this in a couple of different ways. Of course, this is going to be a vector function. We can either write it as parametric equations or we can write it as a vector valued function. And all of these are going to be dependent on where this is in time. So if we look at this point here as it moves in time on the XY plane, I can describe that in terms of this vector and how it's moving in time. And notice that vector at different points in time, and you can look at the animation in the chapter contents, you just get to watch this dot and that vector move at these different points in time, and that's what happens in that. So then we'll go on to the next where we're actually going to write some of these equations. So this is a way to represent these vectors as they're moving in time. I have a beginning point here, P naught, and this is going to be my vector function. We could also write it in terms of parametric equations, and you can see that I'll be able to go from one to the other, and I'll demonstrate that here in just a minute. First off, they want me to find an equation of a line that passes through this point, and here is the vector of how that is changing in time. Here's our definition. I have this point, and if I want to write this as a vector function, which I have all of this information, I can then say that R of t equals this R naught plus t, and then this vector. Let me go ahead and write that each of these is a vector. And how I'm going to write that is just the beginning point, which is that P naught, so that would be the 1, 2, 4 point. That's where I begin, and in time it changes as this 5, -3, 1, and putting that all together in one vector function, it would look like just 1 plus 5t, and that is your I direction or your x direction, whichever you like to say, and then 2 minus 3t, and then 4 plus the 1t. And there I've written it as a vector valued function. So if I would like to look at it in terms of what it would look like parameter wise, I would just say that x equals the 1 plus 5t, y equals the 2 minus 3t, and z equals the 4 plus t. I can write it in any of those fashions, and this is the vector valued way to represent it, and this is the parameter way to represent it. Let's just look at the picture. Here's our beginning point here at 1, 2, 4, and this is what the vector looks like in time. What they've drawn here is just its projection into that XY plane. They haven't really discussed that yet, but we're going to do that in the next problem, so I'll go there for the next one. Alright, for problem A, what I'm supposed to do is I have a beginning point and an ending point. I'm supposed to find the equation of L, and I want that vector and how it's changing in time. So the first thing I will need to do is get that v vector, and that v vector is just going to be the line P naught P 1, and if you'll remember back how I'm supposed to do this, I'll take each of the different components and do the P1 minus the P naught for each direction. So 4 minus a minus 3 would be 7, and then 2 minus 5 be -3, and then -1 minus 8 is -9. So I now have the vector component. Now I'm just going to follow the same thing that I did last time and get what that vector looks like in real time. So I'm going to be finding my R of t, how it happens in time, and that is just R naught, its beginning vector plus time multiplied by that vector v. Oops, I was going to write those points down. Don't want to do that. Alright, not yet anyway. Okay, I want to do it now. So the R0, that's my beginning point, so that would be that point in space -3, 5, 8, and then plus t times that vector 7, -3, -9, and I get my ending vector here is -3 plus 7t, and this is how this vector is changing in time. Oops, I'm going to write a minus. I'll pause you. Alright, so now I've got that written down. That's the A part. It's finished. Here is that beginning, let's see, yeah, here's the beginning point, here's the ending point, and that vector would be moving along through here in time. So at the beginning point it would be here, and then R0 here, and then R of 1 would be here. They want me now to do the projection onto the XY plane. What that would mean for the B part is I've got to do these two separately. I'm going to do it for XY and then I'll do it for XZ. When I do it for the XY plane, that means the Z component is 0. So what I have for the XY plane projection, that means I have that X equals -3 plus 7t, and Y equals 5 minus 3t. I'm supposed to find the equation of that line projected onto that XY plane. So I'm just going to get rid of the t parameter in this case, and then I'll just have a line that's a function of both x and y, and that will be the equation of the line. So I'll do that algebra. Okay, I've completed that algebra, and I get, here's the projection of that line, and I believe they show that to me in this graph right here. This is the projection of that line in space, so you can see it on that XY plane. Here's the shaded section here, and then that shows its shadow in that real space. So I'm going to do the same thing for the XZ plane. I'll set the Y component equal to 0 and then get rid of the T parameter for the X and Z, and that will get me the equation of the line on that XZ plane. Alright, and here's after completing that algebra, and I get this blue line here. This is that projection of our original line in the XZ plane, and there he sits, that part right in there. On to the next. Equation 3 is very similar to, or example 3 is very similar to example 2, in that I have a beginning point and an ending point here, and I'm supposed to find the vector. I'm going to do just what I did last time and take each of the P1 components and subtract to find what that vector is. So that'd be 0 minus 3, that'd be a -3, 5 minus a -1 would be 6, and 2 minus 4 would be a -2. So there's my vector V. At my beginning point, I will write down that it is 3, -1, 4. Using this definition is what I'm doing, and then t times my vector v, and putting all of this together I can write that r of t equals, writing in one set of vector points here, 3 minus 3t for the x component, -1 plus 6t for the y, and 4 minus 2t for the z component. It's of special note that if you were to look at r of 0, notice that you would get, that means t would be 0 in each of these cases, you would get 3, -1, 4, which is my r of 0 vector. Notice there he sits right here. Now let's look at the vector r when t equals 1. So let's plug that in here. 3 minus 3 times 1, that's a 0. Negative 1 plus 6 times 1, that's 5. So that right there. 4 minus 2 times 1 is 2, so that would be a 2. Notice that this vector is our ending point right there. Here's this line segment, and here's our r of t, with it happening anytime, any point where it might be from time 0 to 1, because it does have an ending point. Here's my ending. Here it does have an ending point and a beginning point. They also did for you in this example, they graphed the projection in the xy plane. They didn't ask us to do that, but there it is if we want to look at it. Now we're not going to want things to just be move in straight lines in three-dimensional space. We have objects that move in arcs and curves, and we can model those arcs and curves with different functions. So you'll notice that what we have here are our r vector, as our point is moving in time, is now being modeled by functions on each of those components, and each one has its own function, and I can write it in either of these two fashions, but notice that this is now a function in time and not something that's just linear. This point can move in both positive and negative directions. If the point is moving counterclockwise, we say that that is in the positive direction because of the orientation of the plane. So let's go and look at one of these problems and see how we're going to solve something of this fashion and see how it's represented. Alright, what I have for you here is we have a curve, and here's how it's represented. Well, you've only got a calculator, and you just don't get to necessarily have this and then some magical picture drawn for you, so you won't really know what it looks like. So what I've done for you is I've shown on your calculator what you'll do. If you will put your calculator into the parametric form instead of just the function form that you probably have been graphing in, then what will happen is when you push your y equals button on your calculator, then you will get, when you push y equals, you'll get something graphed. You'll get a representation that looks like this. So each of your x's and y's would come up as some function of t. If you will push the, in order to get whatever variable you want up, you have a button on your calculator that looks like x, capital T, and theta and n. And if you'll just push that button, the appropriate parameter will pop up for you. You don't have to go and try to find that capital T. Also, I just hit mode to get to this screen. And next, I want it to graph this, but I want it in some window that will look nice. I knew that for the first part, this problem has two parts. For the first part, I just wanted t to vary in between 0 and 2 pi, so I keyed 2 pi here, and it pops up the numerical for that. T step, I had it go in terms of pi over 12, just so that my curve would be smooth. You can play with this and see what happens if you have this smaller. It just looks a little off. I knew that my x parameter was going to vary in between 4 and -4, so I just wanted it to sit inside my screen nicely, so I told it 5 and -5 and count by ones, and then the y min and max, I saw that the y's were going to vary between 1 and -1 and said, alright, there's how I made my window. And this is what I got. Now what's happening is, if you will look at, I only graphed this in the xy plane, I set z equal to 0, I can see what the shape is, and this shape is going to be an ellipse. So in the xy plane, I have an ellipse. Now this ellipse, as t goes from 0 to 2 pi, as t goes from 0 to 2 pi, let's see what happens. If t is 0, notice this thing is 4, and then as I wrap around, it moves in this direction, which means that it is moving in the, if you choose t to be, it goes from 0 to 2 pi, so pi over 4, and walk with it from there. You'll notice, and it really, if you were trying to play with the numbers, you wouldn't know which direction it was going, but just pop in a pi over 2, and you'll see that it gets to be a 0, and then after that, then your cosine becomes negative because of what's going on with your cosine numbers. So just play with it a little bit, and you'll see that it is going in this counterclockwise direction, so I know that it's moving in that positive direction. Then the z component, notice that as t gets larger, this value here gets larger and larger, which means that this is moving in, from wherever it starts, it moves in this upward direction. So I'm making an ellipse, but I'm moving up at the same time. And this is a helix. And we can put in this, both the beginning and the ending points, just plug in a 0 here. Let's write down each of those points. I'll plug those in. So let's note that my r vector at the very beginning when time is 0 is at this 4, 0, 0 point, and at the end of its rotation it is now back where it started, as would be here, except for that it is moved up, and that's you can see that by the fact that the z component is up 1 from where it was. Now let's look at what would happen from negative infinity to positive infinity, and what would happen there is just that this continues to wrap around and go up, and then it doesn't start at just time 0. It also started from down here, so it just is this spiral wound, kind of like what a slinky looks like. So it is a helix that continues in both directions endlessly. So, all right, endless helix. And this is basically one rotation of a slinky. You could get just one circular to there. And that's how I would describe that curve. Alright, in looking at this next curve, here is where the point exists at any time in between 0 and 2 pi. I had my calculator graph in the XY plane. That means the XY plane, it's going to make a circle. I did, in order to make my graph really nice, I did hit zoom square just so that my screen was a square and not a rectangle, and I could see that it was indeed a circle, because it's hard to see on a rectangular screen, and you have to, if you really want to see what it looks like, you'll have to hit zoom square to get that. Then notice that these two look the same in the XZ plane and the YZ plane, but notice that this is a YZ plane and this is an XZ plane. So I want you to notice that this green is along the X and Z plane, so there's that projection onto the XZ, and then this red is along the YZ plane. So these two are actually going in basically orthogonal from each other, because one is in the XZ direction, the other is in the YZ direction. So what this point does is it actually kind of makes a roller coaster as it moves along, and if you go to the animation, which I'll just go ahead and do that, we can watch this point move in 3D space. And let me get this thing going. And we can watch this move in three-dimensional space. And watch the point as it moves on and on. It moved from 0 to the 2 pi. One more time because it's super cool. I'll get all my project grids on here and I'll tell it to play. Notice it goes back to the beginning of where it started from right there. Nice. The formal description of this curve is just looking at this R of t without the z component, and then describing that it's a circle of radius 1, and the fact that the z component varies between when you plug in 0 and then you plug in 2 pi. You would see that the z component varies between negative 0.4 and 0.4, and then it would make this curve oscillate 2 times because of the 2t in here. And the result is the fact that we have this roller coaster type shape going on. Next, we're going to look at a slinky curve. This one's fun. I have projected this curve. This is something like what you'd be given, and all you will do first is you'll just have to see what it looks like in the XY plane. Then you want to see what it looks like in the YZ plane, knowing that it is moving in both this XY direction and then moving up and down. That's the XZ plane all at the same time, in addition to moving in this YZ plane. So it's making these loop-de-loops here. And in order to further visualize what this looks like, I'm going to use their little animation to show you what the end result is, moving in both the X, Y, and Z directions all at once from time starting at 0 to 2 pi. Groovy little animator that they have here. What I need to do is just hit the play button and watch it happen. And you can see it moving in both the X and the Y direction while it's moving up and down. The up and down is the Z, and then moving in both this X direction and the Y direction all at the same time, and you see that it makes a slinky kind of curve. So let's see how we would describe this slinky. Alright, we would say on this one that from 0 to 2 pi what's happening is our curve has 20 oscillations, and then this R moves from -5 to 5 due to this X component. And then for the Y value, it also is then going to move from the same -5 to 5. The Z component, however, is moving from the -0.4 to 4 over this 20 times, and then we have this coiling type shape as we saw through the animation. In order to find the limit of a vector valued function, it is just the standard definition of a limit. We are going to look at each of the individual components here, and we're going to see what happens when we plug in a 2. And if you can plug in a 2 just as you do with the normal limit, that's what you'll do. So I'll write that down. Alright, just plugging in that value for 2, I end up with this vector for the limit. The next one is, I'm going to see what happens, and if any one of these fails to exist, then the limit fails to exist. I'm going to see what happens as t approaches infinity, and I can already note that even though I can plug in infinity here for this e to the -infinity, and I know that goes to 0 because cosine and sine are oscillating, that limit doesn't exist. So for the b, I'll write does not exist, and the reason for that is because the limit of cosine and sine as t goes to infinity fails to exist. C, at which point is R continuous, just check each one of these different functions, and if it's all continuous, then you can say each one of these different components of the function. See if it's continuous. Because this is continuous everywhere, I can say that this is continuous for all t. So the R vector is continuous for all t. And they give you a picture of what this particular function looks like, and you can watch that animation if you will. And if you have any questions, see me at the Collaborate.